comes to the forefront when we find that a neural network is capable, or we find that the neural network is capable of tracking time variations. Then we call it to be a dynamic neural network. There should be some topological feature. There should be some characteristic there in the network that will permit the network to deal with the time varying properties of the samples fed to it. We can have the dynamic characteristics in a feed forward NN by planting their memory or time delay blocks, say in the front end of the network or the back end of the network. So such networks can track time variations and therefore are used for dynamic situations. One such network is known as the time delay feed forward network. So one such very common dynamic network is called the time delay feed forward neural network. Now this diagram shows the most common or the most fundamental structure of the time delay neural network. This particular structure is used by the MATLAB to generate a time delay neural network. So here we find that there at the pattern feed layer, we will have some delay blocks, z to the power -1, z to the power -1, z to the power -1. So these are all delay cells. These are memory cells. So when there are delay cells, when there are memory cells, they're at the front end or the back end, we can call that to be a time delay network. We can call that to be a time delay neural network. Now, this particular delay contributes in providing the network the capability to track time variations. So this part will develop the capability in the network to deal with time variations. So once you have these delays, the path will be scaled by the connectionist weight W, and they will go on to the middle layer. There in the middle layer, layer by layer, there will be summation block. Then finally there will be an activation shell that will finally give us the result. But again, since we need to deal with a multi-class problem, therefore there will be a further scaling up of the response by one more weight matrix, W11 raised to the power of 2. Then finally we have the backend layer. That particular backend layer will be generating the response. So these two functions depict the response of the middle layer and the backend layer. So these 1 and 2 will denote the responses of this layer and this particular layer. So these are just denoting the symbols representing the middle layer and the backend layer. So if we simplify the structure and see it in a more reduced or shrunken format compared to the recurrent neural network structure that we saw in the last lecture, we will find here that there shall be one tap delay line there at the front end. So there will be one tap delay line. We might recall that we saw in the previous lecture, that in the case of the recurrent neural network, we found there can be tap delay lines in the forward parts. There can be tap delay lines in the feedback paths. There can be tap delay lines in the local feedback path. There can be tap delay lines in the global feedback. So here, but in this case, we find here clearly that there is a tap delay line there in the front end. There in the front end or in the pattern feed layer. So a tap delay line there shall be generating the delay function that will be responsible for tracking the time variation that the samples might have, and this will permit this network to function like a dynamic neural network. Now let's see a very simple program in MATLAB, through which we find how the tap delay line or how the tap delay line can be used to design a time delay feed forward structure. So we here have a tap delay line with delays from 1 to 10. And then we have 15 neurons there in the middle layer. So uh, uh, we have taken here a built-in function by the name time delay net. The first part shall be tap delay lines with delay between 1 to 10, and this particular 15 will mean that we will have 15 number of neurons there in the middle layer. Now this will be the number of epochs that the network will be trained to. So now this is the function through which the network is trained. We have here a pattern here. We have here a target, and then we have one more term here, pi. That particular pi will be responsible for giving some previous state know-how. So this particular variable will hold the train network structure. So then we can see here one more such program where we have here defined a variable that takes random numbers of size 1200. Then we have here a pattern P. We have here a target T. Then we now show here how to define a tap a time delay feed forward structure. So this particular feed forward structure can take the pattern and the target simultaneously. That is now meant to have delays between 0 and 1, and it has five number of neurons there in the middle layer. Now this particular network is meant to run a epoch of 1000. Then here shall be the training. Here shall be the function for carrying out the training. Here is the way to simulate the response from the train network. And if we want to find the root mean square or the root mean square difference, that can be done or that can be found from this particular syntax. So while we run it, so if we run it, a mm, uh, structure of that type shall come, that will show us the thousand number of recursions completed, the performance goal reached, so on and so forth. This will show how the network can be formed, configured, and trained. So this particular simple program shows us how we can design a time delay neural network. Now we can find out, or we quite frequently see that the time delay neural network is used to deal with the time series data, and then do prediction or forecast based on time. So the structure therefore is quite significant. How we formulate the structure, how we configure the structure to generate finite dynamic response to time series data. That part is quite significant. Now let's see one more such program, a recent one. How the more recent MATLAB, that is the MATLAB 2020 version, supports it. We can find out from this particular syntax, or this particular uh, program. Now we here take a simple time series data from the repository, MATLAB repository. Then we fix it. The pattern and the targets are separated out, and we take a series that shall be used for doing the regression, or for doing the prediction separately. Now we here first define a time delay structure with delays between 1 and 2 seconds. Then we have here 10 number of neurons. They are in the middle layer. Then we now use the preparates function to condition the network, to condition the patterns, to condition the target, as we have spoken about it in our previous lectures. How data is conditioned to make the training more reliable, to make the training more robust. So once we have prepared the data, we can now train the network. So train net. So these are all new forms of uh, derived data from the preparation stage, from the pre-training preparation stage. So they are fed here. Now we can here view the network. Then we can also calculate the network's performance by the use of the perform function. So we give uh, all those parameters that were derived from the preparation stage, and then we can here find out the performance of the network. Now if we want to run it for a 20-step look ahead, so we can do that. Run it for a 20-second look ahead mode. So here this is a syntax for that. Closed loop. So net capital X F, capital AF, those are derived from these particular preparatory stages, and then we can view the network. So uh, mm, while we create the network and train it, a structure of that type shall be visible. That will show us clearly the training taking place. Then we can see its performance. So convergence curve, we can find out that uh, during the training, the learning is fast, and in less than 10 number of cycles, we find that the goal is being reached. We can also find that there are separate curves for the validation part, for testing part. And then we see that during the training part, the best limit is crossed in less than 5 number of training cycles. Now, if we want to see what shall be the response, we can compare what we have generated, or what the network has generated, and what is the desired response, or the target. When these are compared, we find that they are fairly close. They are closely uh, resembling, or they match very closely. So we find that the difference for all the time, for 70 slots of time, the difference is less, very less. So we find here that uh, this particular time delay neural network, designed with the tap delay line, is quite reliable, and in very few number of cycles, it generates a high level of reliability. Now we can find out one more case where we see how a time series uh, prediction can be done for a far IR laser in a chaotic state. We will use the first 1,000 points there in the time series to predict the next 100 points. So one more such case where we can use the time delay feed forward structure for generating a time series prediction. So we can see here that we have taken a data set from the MATLAB repository. We have taken here 600 data. Then we have here configured the uh, time delay network with delays between 1 to 8. We have taken here 10 number of neurons. They are in the middle layer, and we have here fixed 1,000 cycles for doing the training. So we now fix here the pattern target, and then we here fix the pi as the uh, set of values that shall be used to do the regression. So we now here train the network, and once we have the network P, then we use the knowledge of dealing with 600 or 1,000 set of data, or 600 number time series data to generate the next 100 uh, numbers of time series data. So here is how the program can be written. So if we see the training time performance, we can find the plots for the gradient descent, then step sizes reach, and then the validation checks. So these are quite comfortably generated. The network's topology and configuration shall be quite critical in generating this particular performance. Then when we compare the present response and target, we find that they are very closely matching. There shall be very close resemblance. So it too also is quite capable of dealing with the time series prediction. It demonstrates a clear dynamic nature. It is capable of dealing with 600 time series points of the laser data, and then use it for subsequently generating the regression of a few number of points. So we find here that the present response and the target response are uh, closely closely matching. So this is quite a satisfactory performance with less number of uh, training cycles. Now, now there is one more network called the NARCs, short NARCs. So this particular network is known as the nonlinear autoregressive with external inputs, ANN, or the NARCs network. This is a very special version of the recurrent network. It has autoregressive feeds. It has a very strong temporal capability. Temporal capability means it can deal with time variation. Quite frequently used for tracking frequency variations. So when we need to track frequency variations in real world signals, real world communication signals, this particular network is quite beneficial. Then it can learn to predict a time series y given the past values of y and another time series x. So that will be the external or the exogenous feed. So here is a syntax called the NUXNet. There is a built-in function called a NUXNet. So this will need the delays, the feedback delays, the size of the hidden layer, the feedback mode, and the training function. So let's see how to train it, how to create and train a NURCs network. So we take here a simple data set. We here use the NURCsnet function to create a NURCs network. We have a delay of 1 to 2. Then we have here a feedback delay also of 1 to 2. Then we use 10 number of neurons for the middle layer. Now we again do a preparation beforehand, a pre-training preparation of the data by this preparates function. Then we train the network. We view the network. Then we simulate the network, and then we try to gauge or keep track of the performance of the network. So if we do the training and we run the simulation, we will find a NURCsnet neural network of this type will be generated. We find that the performance is reached in roughly about 686 number of training sessions. Then if we find out the performance of the network, we can see that its gradient value, the step size, and the validation checks are successfully done. Once the number of cycles required for reaching the performance goal is sufficient at the zone value, then we can check its learning curve. So the learning curve show that its convergence is quite satisfactory, and the blue colored line, that is the line generated during the training part, is reached or has a very steady convergence. And then there are separate curves generated during the validation and during the testing part, while the best performance is crossed at around 450 cycles, 450 cycles. Then we can show here a regression uh, curve generated, or a regression response generated by the train network. This clearly shows that the network is capable of the use of its learning to generate a separate response uh, from a separate feed, from a separate pattern feed. So once it learns a particular set of patterns and is passed through the training to do the mapping, then by the use of that particular learning, or by the use of that particular training, the network is quite capable of taking a completely separate but similar set of data and generating a separate yet similar type of response. So here we see that the network's regression plot is quite satisfactory. The regression plot is showing us clearly that there are clear signs of reliability, or reliability demonstrated in doing the regression. So if we compare the response with the target response, we find that the difference is quite small, very small, in fact, and and the and the testing and the training time target and the outputs are very closely matching each other. So this is quite a satisfactory performance, or a satisfactory response generated by the network. Then we can see here how to create a NARCS network. So one more form of the NARCS network, and how that will look like. Then there is one more network called the distributed time delay neural network. We will find here that the tap delay lines will be distributed uh, in the layer 1 and in the layer 2. We have found previously that the tap delay line for the time delay neural network, the most common time delay neural network, had the tap delay line in the layer 1. But in the case of the distributed time delay neural network, we find that the tap delay line shall be distributed in both the layer 1s and the layer 2s. So it will have a mm, uh, a greater dynamic range. It will have more reliable dynamic performance. It will show more resilient or more robust temporal tracking capability. So we see how to separate out two frequencies. So we will see here that the distributed time delay neural network is trained to recognize two separate frequencies. This is quite significant for the fact that a signal with a frequency is a real-time signal. So that particular real-time signal with variations in the frequency uh, can be tracked and recognized uh, uh, successfully by the DTDNN. So you can see here that the program shows a time scale. Two separate signals are created. Those are here. Those are grouped. And once we have done the grouping, y1, y2, y1, y2, two separate sequences are created, but those are combined to form a single vector. Then we find that the labelings are created. Labels are created to show So the class, two separate frequencies. Now here is one T1 shall be one class of frequency, T2 shall be the separate class of frequency, or the separate signal with a separate frequency. So the labeling now will be done as T1, T2, T1, T2. So this Y1 shall be mapped to T1, Y2 will be mapped to T2, Y1 will be mapped to T1, and Y2 will be mapped to T2. So two separate frequencies are being mapped to uh, two separate classes. Now here is the training. So once we train it, so we can use the training function train BR, or we can use the training function LM. So once we do the training, so here is the pattern, here is the target. So this one will be this con2sig will be generating a sequence count for the vector content in Y. Same way, T for T, the sequence count for a target shall be generated by this PNT. So PNT now will be the pattern and the target. Then we will be here creating a distributed delay network. So the first set of delay shall be between 0 and 4, and the next one shall be between 0 and 3. We then further have 5 number of neurons in the middle layer. So now we do the training. We here fix 100 number of training sessions. Then this one will be doing the training, and then finally we will be generating the response from the simulation by the use of the train network and the pattern. We will find out that the two frequencies are separated out like this. So here is one uh, frequency group, the same frequency group there, and here is the second group of frequencies. So the two separate frequencies are clearly recognized and placed in two separate classes. So this is how the distributed time delay network can be used for recognizing frequencies. Now we here will be finding out how we can program the recurrent neural network. Last time we found that the recurrent neural network is a feed forward network that has a feedback pass 2, through which it will be generating the dynamic behavior, and hence is found to be quite capable of demonstrating temporal processing. We can find that the recurrent neural networks are built by the use of the time delay structures, by the use of the tap delay lines, by the use of the local and the global feedbacks. We can find that the recurrent structure can be simple one, can have a distributed recurrent structure, can have a fully recurrent structure, can have a partially recurrent structures. We can also find that the FIR and IIR filters are also used to generate the recurrent behaviors. Last time we saw these structures for the reference part. I am here showing one more time that how the recurrent structures are built, since this part is quite significant while we design the recurrent neural networks. So we here find that the recurrent neural networks have or show nonlinear dynamic behavior. They can be used as continuous time system or as discrete time system. They can be also used for real value and quantized sample cases. So these are few recurrent structures. The first one is called the simple recurrent structure, where we can find that the feedback path can be a localized one from layer 1 to layer 2 or from layer 3 to layer 1, but not in all the layers concurrently. And then we can find that the recurrent networks can have global feeds or can have the feedback paths coming from the back end to the front end, to all the neurons. So that will lead to more capable or more resilient temporal tracking capability, but that will again put huge stress on the computational load. Now we here or see one very simple program to train or to first create a recurrent neural network and then see how that can be trained. Now to train or to create a recurrent network, we use the built-in function new ELM. So new ELM. So here we see that a new ELM is used with the pattern and the target. So here are the pattern and the target vectors specified. Then we generate a few sequences. A sequence mapping means to generate the time sequence track for the pattern P and for the target T by the use of con to seek built-in function. So that is for both the pattern and the target. Next, we will be we can now use the new ELM function to create the network with the with the pattern and target and 20 number of neurons there in the middle layer. Then we use the train function to do the training, and then we use the sim function to generate the simulated response by the use of the net function. Then there is one more recurrent structure called a layer recurrent network. So this particular layer recurrent network has a localized recurrent behavior. There is a feedback path with a single delay around each layer of the network, and that will not be seen in the last layer. So here we have a layer-wise recurrent behavior. Now, how to create a layer recurrent network? We see here that the P and T, that the pattern and the target are generated or are taken to be two separate vectors. Then we generate the time sequence count for the pattern and the target by this PSEC and TSEC. Then we generate the layer recurrent network by this new LRN. Then we train it, and then we simulate it. We find that the convergence curve is a steady one, and it reaches the destination or its fixed goal quite steadily. The learning is quite steady one. Now we should be also familiar with the radial basis function, how to create the create the radial basis function. Since in the last last lecture, we have talked about the radial basis function in quite some detail. We can use the new RBE function to create the radial basis function. Now simultaneously, while we are familiar with the radial basis function, we can also become familiar with the generalized regression network, that is the GRNN. So both, and then again the probabilistic neural network. So both the GRNN and the PNN, these can be configured or can be formed by the use of the function new GRNN and a new PNN. So here are two such syntaxes shown. So in the first case, we find how the RBE, the new RBE is used to uh, to create a radial basis function. Then we see further that the new GRNN function can be used for the creation of a generalized regression network. And we further also see how to create a probabilistic neural network by the use of the function new PNN. Then we come to the self-organizing map. So this is one more network, though it is an unsupervised network. We have talked about SOM in our previous lecture. SOM is one more network, though being unsupervised, or though being designed for the use of the competitive learning philosophy, to demonstrates the dynamic behavior. So SOM is known for its dynamic behavior, but with the unsupervised learning paradigm. The previous networks have supervised learning paradigm. So we can skip this part and then straightway come to the unsupervised learning. We have talked about it several times, so we will not spend much time in this part. But we need to remember here that in case of unsupervised learning, there will be no prior reference. So there shall be a self-learning. There shall be some sort of competitive learning, and the network will try to create some groups by finding similarities uh, between the samples, sets of samples. Yet the common tasks are clustering, vector quantization, and feature extraction. So these are the common parts which are characteristic of the unsupervised learning. So we might recall that unsupervised classification is done on the basis of creating clustering of the patterns. No a priori knowledge shall be there to view or to generate the clustering or the grouping. We will find here that as the training continues, the learning grows, and that will help in generating better reliability in the formation of the clusters. And we should remember that clustering is a mechanism of of grouping content by following some similarity, and then discarding the content with marked dissimilarity. The governing principle is that this particular network follows a winners take all uh, take all uh, type thought. So there shall be continuous competition between the neurons to take a sample from the pattern vector. Now this is done by finding a similarity match that can be based on the Euclidean distance or several other distance uh, parameters or metrics. So so the neuron that has the closest match with the sample of the pattern vector will take the particular sample at a given point of time, but that can change as the training uh, training proceeds. So while the training goes on, the learning goes on by following the competitive learning method. We find that there will be weight tuning, the change in the weights taking place, and by that change of the weights, there will be a restructuring taking place in the network's topology. There are a few marked steps. Step one will have the definition of the weights. Uh, Weight will be generated by taking the present value of the weight, then a step function, then a difference between the weight and the pattern vector x. The weight will be WR. Then there will be a weight normalization, and then uh, step three will be weight uh, uh, regrouping, or the topology grouping, rearrangement. Then finally, once that part is done, the weights will be changing continuously. So while these steps go on, the clustering will take place in this particular form, where there shall be cluster centers created, and the cluster centers will have its own weight sets, W1, W2, W3, for cluster 1, cluster 2, cluster 3. So this is how the regrouping of the topology from the beginning to the end will will look like. The regrouping, the reconfiguration of the network while training is on, will form the clusters, will have the grouping of the uh, common samples, uh, linked to the neurons with weights that has the closest match, closest or the smallest uh, uh, Euclidean distance value, will form the reconfigured neighborhood, and that will help in facilitating a competitive learning, and is driven by unsupervised learning. This creates dynamic behavior, and the SOM is known to deal with speech uh, samples, speech processing domain. SOM is quite successfully used, and researchers have reported it. So how the network will look like finally. from the pattern feed to the creation of the neighborhood. This will be a two-dimensional neighborhood created due to the continuous regrouping of the structures that will take place while the learning goes on, while the training goes on. Now there are several dissimilarity matrices, though the most common one is the Euclidean distance. There can be Minkowski's metric family, uh, Tanimoto distance, Chebyshev, and so many of them. So let's see how we can do or create competitive learning networks. Now, SOMs are known as the competitive learning network. One of the more popular competitive learning network is the learning vector quantization network, where the first part is based on competitive learning or unsupervised learning, while last part is based on uh, supervised learning. Now here is a structure of the competitive learning. So here's a layer one. So this particular layer shall be the pattern feed layer. We will have here the pattern vector P. Then next part shall be the competitive layer. This particular n-dist will be a function that will be calculating the distance measure, the Euclidean distance. That particular neuron, which will have the closest distance value, will take that particular sample that will be scaled by a weight W, and then will be linked with a bias, and then that will take part in a clustering done by the C. So this will result in a grouping here. So we can find here that the new C function, syntax new C, can be used to create a new competitive learning layer. The train function can be used to train the network with the pattern P. Then we can find Y to take the simulated response from the train network by taking the pattern P, while this YC will take the class codes. So this function vec2int will be generating the class count of the Y, all the values generated by the train competitive network for the pattern P will have some class code. So that will be shown, or the class code linked with Y can be generated by this vec2int function. So here is how that will look like now. Since the SOM is in a neighborhood structure, a two-dimensional structure, so we find that the neuron in 3 cross 1 location will be in class 1. The 2 cross 2 neuron will be in class 1. Then 3 cross 3 network neuron shall be in class 1. Then 3 cross 2, 2 cross 4 shall be also in class 1. Therefore, we find that 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 uh, that the three particular neighborhood points with 3 to 3 to 3 to class counts uh, shall be here selected for the clustering, for the grouping. So you can use. There are several other functions that are used with the comparative learning, called the next then the net sum, then the compet and transfer function, and so on and so forth. So net dist is the negative distance weight function, while the net sum is a function that is that is required to find the sum of the weighted inputs and the biases of a comparative layer. Then the midpoint is a weight normalization function. Then init cont is a bias initialization function. Trains is a sequential training function. Then train er is used for random order incremental training. Then train b is used for batch training. Then learn nk is used for Cohen weight learning function. Then learn con is a concise bias learning function. So how the self organizing feature maps will look like. Now, SOM was meant for doing dealing with features. Therefore, the term feature map comes. So we can use functions like grid top, hex top, ren top that will create different type of network topologies for the SOM, and those are required to formulate network structures to suit a particular purpose. So here are the SOM's neighborhood types. So a grid topology will look like. So we can have a 6x2 grid top generated by this grid top function. Then we can plot the SOM's grid top topology by the use of the plot sum function. Then we can also find the weight values, and then we can also determine the distance between the location points. So the grid top function is a grid-like topology that will be used with the SOM. Then the hex top will create a hexagonal topology by calculating the neuron locations. Then the ren top shall be used to create a topology where the neurons are placed in a random format. Then the SOM will use this function primarily to calculate the distance, the Euclidean distance, which follows a syntax like this: d taking value of square root of sum of and the x minus y square. So the man dist can be one more such distance term or distance metric, that is the Manhattan distance. Then link dist to calculate the distance function for the distances between the neurons of a layer by noting their points where they are. So here is the SOFM topology, same like the competitive layer. So it is also a competitive layer topology, but we can find here that at the last layer there will be a compnet function. So this particular compnet function will be generating the unsupervised learning and will create the competition to select the winner neuron that will take the sample value and then form the clusters or from the grouping. So a particular function or uh, a small small problem here shows that from a random number or a pattern created by the use of random numbers, p with random numbers is now used to to configure a SOM by the use of uh, the new SOM function that has a uh, range, or that takes values between 0 and 3 and 0 and 2 in the first part. Then we'll have a neighborhood of 4 by 6. So we first plot the points where these will be, and then we will be doing the training. And then once the training is complete for 100 number of recursions or iterations, we can do a plotting with marker size. So how the network forms, or how the selected neurons are linked, or how the networks uh, how the network uh, is here, or how the topology will build up, or how the neighborhood will be formed by the use of the selected or classified neurons, or the neurons that are taking the sample values, how the network builds up. So here we can see. So the red dots will be the cluster centers, neurons that will have the grouping taking place around them. So then the map will be linked. So the map linking will be creating a network here, and this is quite the resultant uh, self organizing feature map. So from this large data set of 2 cross 200, we have a very uh, few number of neurons finally coming out, which will have certain cluster centers, or which will form the cluster centers, where the most relevant part of the data will be sticking around. So through this way, we can find that the SOM is uh, very resilient in generating uh, dimensionality reduction. So the SOM is quite capable of doing feature selection. So from large data set, by the use of the SOM, we can reduce the feature structure, or we can reduce the data size, and then generate a uh, particular feature set, the most relevant, or the most reliable feature set. But nowadays, with the help of by the due to the growth of deep learning, feature selection is no more a factor. But in the case of the previous generation neural computing, for the feature selection part, this was a very um, reliable means, or a very sought after means of selecting or generating features from large sets of uh, sets of data, primarily while people dealt with uh, satellite data. So to create the most relevant part of the data, huge size of data, this is one of the most reliable, or or promising, or uh, sought after means of doing dimensionality reduction. Then the the latest version of the MATLAB, that is the 2020 version, shows a SOM or has a SOM compiler that will be more, that is found to be more resilient or more proficient. So we see here we can take a simple class data set, then we can form a new SOM with a topology of 8 by 8. Then we can train it and then plot it. Then once the training goes on, we can find that the neighborhood of the selected or the most sought after uh, or the neurons that have won the competitive learning phase have formed neighborhoods, connected neighborhoods, and have clearly uh, done a done a cla- done a clustering. Around the clustering, sub neighborhoods are formed. A bigger neighborhood is there, then sub neighborhoods are there. So this shows clearly that the SOM can be used very well for generating clusters that have that demonstrate similarity of features, similarity of characteristics from huge data sets. So if we uh, train it, we will see that the network connections builds up, and this particular building up and reconfiguration will be crucial in determining how the network finally will look like, how the clustering will take place finally. So SOM's neighborhood connection diagram will be something like this. So the weight distances are quite critical, because the weight distances will determine how close the data are, how close the samples are to the uh, to the grouped neuron, to the neuron to which the sample is grouped or is clustered or is placed. So weights from one of the samples from the first feed and the weights from the second feed, these will show us color variations, and the more close the samples are, or the sample sets are, they shall be placed close to that particular grouping, and that way the neighborhood will build. Then finally we can see from the results that the sample count, which sample count is grouped to uh, uh, which particular neighbor, which particular neuron in the specified neighborhood, that can be also seen. So we can see that one specific sample is placed in here, one specific sample is placed there. So this way the complete diagram of the sample placement, neighborhood wise or SOM's neuron wise, that can be also seen from the uh, trained structure. So prior to uh, prior to summing up, or I sum up. So in this lecture, we have talked about primarily the dynamic uh, uh, neural networks. We should remember that the neural network shows dynamic behavior from its capability to deal with time varying signals. So if it is capable of dealing with time varying signals, we can say that the network has uh, temporal capability. So with temporal capability, the network can deal with speed signals, real world signals, time series data, weather data, financial data, so on and so forth. So where there are marked dependence on time, we need special networks which can link samples with time. We can that can keep track of the time variation and the link with the sample. So for these sort of purposes, we find that three categories of networks are suitable. One category is called the time delay networks. Then the second category is a recurrent neural networks, and the third one is a SOM, self organization map. Now the now the time delay networks, they can have the the depth delay line in the first layer. Sometimes we find that the depth delay lines can be in a distributed form. So if it is in a distributed form, we can call it a distributed time delay neural network. And in case of the recurrent network, we find there are several variations. Recurrent networks can be simple recurrent, can have simple recurrent structures. They can have partial recurrent structures. They can have fully recurrent structures. Recurrent structures can be local. Recurrent structures can be global. We can also find that the recurrent structures can be uh, layered. So if we have a recurrent structure confined to a layer, that can be called to be a layered recurrent network. Now, recurrent networks are trained primarily by the use of backpropagation in time and real-time recurrent learning. NARCs is a very special version of the recurrent network, and NARCs is successfully used for dealing with nonlinear dynamic phenomena. Then SOM, self organization map, SOM is a unsupervised network, and the SOM is used mainly for dimensionality reduction, but due to its competitive learning nature, SOM 2 also demonstrates very prominent dynamic behavior. So these are some of the dynamic networks that are useful for real-time conditions. So I would now like to request you all to raise questions if there are. So I thank you all. I shall be sharing the slides with Dr. Kaplan, and I will be requesting you all that you can try a few of these in the MATLAB domain. You will all like it. These are all very satisfying things. You will derive lot of pleasure by learning this and trying to program them a few for real world purposes. So thank you all. Thank you.